Now, let us see Planck's blackbody radiation formula. So, Planck was working on the radiation emitted by a black body, and after so much calculations, every time the formula he got was not matching with the experimental results. So, finally, he applied the idea that perhaps the energy may not be continuous, but may be in quantums, discrete values, and then he started working out with the discreteness of the energy, and finally he got that formula which we today known as Planck's blackbody radiation formula, and that matches with the experimental findings. So, let us see this. So, let us see Planck's blackbody radiation. Planck applied the idea of quantum of energy to explain the radiation emitted by a black body. So, the previous workers used the energy to be homogeneous, continuous. So, according to the theory, the energy exists in quanta or packets, so which was later used by Einstein as photons. So, these quanta or packets was later used by Einstein as photons. So, just Planck used the idea that the energy exists in quantas and packets. According to the theory, the energy exists in quantas and packets, and previous the idea was that the energy is uniform. So, now there is discreteness of the energy. So, with this idea, with this new idea of discreteness of energy, Planck derived a result of the spectral emissive power of a black body at a particular temperature. So, according to the theory, the emissive power of a black body at a particular wavelength is 2 pi some constant C1 by lambda to the power 5, then exponential means e to the power C2 by some lambda T, the temperature, minus 1, where C1 and C2 are constants. So, this is the expression what we got for Planck's law of black body radiation. So, this law is valid for a black body. So, such a radiation law, the spectral emissive power of a real body, the spectral emissive power of a real body, that is E lambda, will be given by EB. So, will be given by that epsilon, that is emissivity at lambda, spectral emissivity times EB lambda. So, this is the emissive power. Spectral emissive power is E of a black body as EB lambda, is this much, and for a real body it will be emissivity, spectral emissivity into EB lambda, where EB lambda will be given by this. This is the expression, and now let us see, we will see its plot, how it is plotted against T, and see what are its characteristics. So, now let us see that what are the features of the graphs plotted from the Planck's radiation formula. So, the Planck's radiation formula, which is emissive power of a black body at a particular temperature 2 pi C1 lambda to the power 5 into e to the power, that is exponential C2 by lambda t minus 1. So, this is the result. Now, suppose I plot this graph. So, while plotting this graph, so here is plotted lambda, lambda increases that side, and here I have plotted the emissive power of the black body at a particular lambda, that is the spectral emissive power. Here we are not interested in the entire spectrum, just the thermal radiation part we are seeing, and suppose here it is not 0 but 0.1 micrometer, and suppose here I have plotted 100 micrometer. So, the initial graph is suppose something like this. So, this is the graph, and you see here this is the graph at a particular temperature, say T1. So, T1. So, this graph, this is the curve, this is the equation which I am plotting here, and for a particular value of T1, this EB lambda varies with lambda, and the graph is plotted like this. Now, you see this graph is very similar to the distribution of molecular velocities, and the idea is that if we have a black body, that is, just imagine a Fairy's black body enclosure, and if we heat it, then when we heat it at, that is, we keep it at a temperature T naught, radiation is moving inside this, and so there are photons or the quantas of energies which are in thermal equilibrium, and just like a gas, these quantas of energy is moving. So, what the Planck's idea was that just like a gas, inside the gas the molecules are moving randomly. So, inside this uniform enclosure of a black body, the photons or the gas or the quantas of energy, of which the energy consists of different quantas, they are moving like that, and the energy is distributed in the entire spectrum of lambda, just like the molecular velocities. So, you will get such a molecular distribution type graph that is here. So, let us now proceed. So, the first essential point of this is, number 1, the spectral emissive power of a black body at a particular temperature, first increases with wavelength, then attains a maximum, and then finally asymptotically decreases to 0. When lambda becomes very large, it decreases to 0. This is the first point. So, you can see this is the maxima. So, till lambda attains this value, it increases and then decreases. So, you can see this, the quantas of energy or the energy distributed in the whole enclosure is similar to the velocity distribution on Maxwellian distribution in a ideal gas. Now, second point, essential point of this is that as the temperature is increased, so this graph goes like this. So, that means second point, the same wavelength, the emissive power, the spectral emissive power of a black body at a particular wavelength increases with rise in temperature. So, in order to illustrate this, I take a particular wavelength. So, this is the particular wavelength lambda naught. So, this is the emissive power, and this increases to this value when the temperature is increased from T1 to T2. So, when the temperature is increased at a particular wavelength, the monochromatic or the spectral emissive power of a black body increases. This is the second conclusion. And we have again a third conclusion. So, in order to explain the third conclusion, let our diagram be clean somewhat. So, now let us plot this curve for different temperatures. So, you see again I am further increasing my temperature. So, on further increment of temperature, you see, now let us see the maximas. You see, these are the maximas, So, when at different temperatures, so this is T3 is, so here T3 is greater than T2 is greater than T1. So, you see if I plot these points, this one, if further is there. So, when we see the maxima of the curve, then we find that all the maximas at different temperatures lie on a hyperbola. That means you can see these maximas of the curve lie on a hyperbola. Thus, we see that as the temperature increases, the maximas of this spectral emissive decreases. So, the important point, as the temperature increases, the wavelength at which the maxima of EB lambda occurs decreases and they lie on the hyperbola. So, all these points lie on a hyperbola that we will see actually is Wien's displacement law. So, these are the characteristics of Planck's radiation formula.